When the engine starts and idles, the transmission pump rapidly fills and pressurizes the converter. The impeller is driven by the engine and turns at crankshaft speed. With the selector lever in the neutral or park position, the turbine also rotates, carried around by momentum of the fluid. When a drive position is selected, the turbine shaft is locked to the transmission output shaft through the transmission gearing, and the turbine comes to a halt. Centrifugal force throws fluid between the impeller vanes outwards, around the back of the guide ring in a forward direction. This is due to the shape of the casing and the curvature of the vanes. With the engine idling and the vehicle stationary, little torque is transferred from impeller to turbine as the fluid flow is too gentle. When the engine accelerates, higher impeller speed discharges the fluid across and against the turbine vanes with greater force. Fluid exits the impeller at high velocity and enters the turbine at its outer edge. This exerts a turning effort against the back of the turbine vanes, which absorbs energy in the fluid, causing the turbine to rotate and transfer the drive to the transmission. The fluid, still at high velocity, now flows between the turbine vanes, leaving the turbine in a direction opposite to impeller rotation. This is due to the curvature of the turbine vanes. Unchecked, this would oppose impeller rotation and reduce turning effort. To defeat this, the stator redirects the fluid. It re-enters the impeller in the same direction as impeller rotation. The fluid strikes the forward face of the stator blades with a backward force, which locks the stator on the one-way clutch. The stationary stator and the angle of the blades change the direction of the fluid flowing between them. The fluid re-enters the impeller at high velocity in the same direction as impeller rotation. It strikes the back of the impeller vanes with considerable force, giving up energy to assist the engine in turning the impeller. This provides torque multiplication. Torque multiplication exists only when there is a difference in speed between the impeller and the turbine. The magnitude of torque multiplication depends on load. When the turbine is stalled, it has a maximum value of about 2.2 to 1. Stall is an operating condition where the turbine is stationary and the engine throttle is wide open, making the rotational speed of the impeller as high as possible. Stall can be approximated to when a vehicle moves from rest up an incline, towing a heavy caravan or car trailer. Instantaneously, as the vehicle begins to move, maximum torque multiplication occurs. At an engine speed of 2,100 RPM and torque at that speed of 100 Newton meters, the torque input to the transmission will be 2.2 times that value, 220 Newton meters. This multiplication tapers off as the turbine commences to turn and increases in speed. This subjects the fluid in the turbine passages to centrifugal force, which slows down the circulation between impeller and turbine. When turbine speed reaches around 90% of impeller speed, torque multiplication falls to 0. Torque transfer from impeller to turbine is then about 1 to 1. This is known as the coupling point. At coupling point, fluid flow from the turbine vanes is relatively low, but it is at high speed in the direction of rotation. The rapidly turning turbine discharges its fluid against the back of the stator blades. This force unlocks the stator and all three elements rotate as one unit. Unlocking the stator prevents turbulence in the fluid and any braking effect on the engine. The revolving impeller carries the fluid with it inside the converter casing. The fluid is rotating around the axis of the converter. This is known as the rotary flow. At the same time, centrifugal force moves the fluid outwards, away from the converter axis. During torque multiplication, the shape of the converter case makes the fluid flow in a circular motion through the impeller, turbine, and stator. This is known as the vortex flow. Combining these two fluid flows produces a progressive circular or spiraling motion. This is known as the spiral flow. In a stalled converter, fluid flows at high velocity from the revolving impeller through the stationary turbine and stator. This results in a fast-moving vortex flow and high torque multiplication. When the turbine starts to rotate and increases in speed, the centrifugal force on the fluid in the turbine opposes the high velocity flow from the impeller. This reduces vortex flow and torque multiplication. At coupling point, the vortex flow of fluid is slight, and there is no torque multiplication. The converter now acts as a fluid coupling. During acceleration or hill climbing, torque needed by the drive shaft can exceed the engine output torque. As a result, the turbine slows, causing an increase in vortex flow. This again causes torque multiplication. The converter automatically adjusts its output within design limits to meet drive shaft requirements. Converter slip and loss of power through the transmission produces heat, which must be dissipated. At stall, a lot of engine output is converted into heat, and this brings the oil operating temperature closer to its boiling point. Excessive temperature rise can produce cavitation bubbles in the fluid, which produces noise and reduces converter efficiency. Some converters use external fins on the case to circulate air through the housing onto the converter. Most automatic transmission vehicles use a heat exchanger in the lower tank of the radiator. Fluid flows from the pump to the converter, then through the heat exchanger before returning to the transmission. In a lock-up converter, the impeller and turbine are locked together when conditions are suitable to provide a one-to-one drive from the engine to the transmission input shaft. Lock-up normally occurs at higher road speeds when light throttle openings are being used. The lock-up piston engages in slots in the turbine and can move axially for engagement and disengagement. Torsional damper springs are built into the turbine piston assembly. When the clutch is engaged, these springs dampen driveline and torsional vibrations. When the clutch facing on the piston comes in contact with the internal machine surface on the wall of the converter housing, lockup occurs. This provides a one-to-one connection from engine to transmission with no slippage between components. In the Sprague-type one-way clutch, the inner race has a central spline. It locates on the stator support shaft to hold the race stationary. The outer race is part of the stator hub. It turns with the stator in the direction of engine rotation. Equally spaced sprags between the two races produce a wedging action to stop the stator rotating in reverse. The sprags are held in place by a spring-loaded cage. The cage moves the spregs together so that when the stator is locked, each carries an equal share of the load. The one-way action is produced by the different radii of the spregs and the curvature at their outer edges. This gradually increases from the shorter radius to the larger. When the stator is turned against engine rotation, it pivots the spregs towards the larger radius and wedges them between the two races, locking them together. When the effort to the stator is reversed, the spregs pivot towards the smaller radius and the outer race glides freely over them in the direction of engine rotation. In the roller-type one-way clutch, the inner race is splined to the stator support. The outer race has wedge-shaped segments, which retain the rollers. In each segment, a waved compression spring pushes each roller towards the narrow end of the wedge. A force on the stator blades against engine rotation locks the outer race onto the rollers, wedged between the two races. Turning the stator with the engine rotation eases the wedging, and the stator rotates with the impeller and turbine. Most automatic transmissions use epicyclic or planetary gears. They are constantly in mesh with each other. A basic planetary gear set has a sun gear which meshes with planet gears, also called planet pinions. The planet pinions, in sets of 3 or more, rotate on bearings on hardened steel pins on a planet carrier, which spaces the pinions equally around the sun gear. It also locates them so they can mesh with an internally toothed ring gear. This means the planet pinions are always in mesh with the sun gear and the ring gear. In operation, their motion is described as either walking or as idling. Walking means that if either the sun gear or the ring gear is held stationary, the alternative driving member rotates the planet gears on their pins. This turns the planet carrier in the same direction as the driving member. Planet gears always turn in the same direction on their pins as planet carrier rotation, while they walk around a stationary sun gear. They always turn in the opposite direction on their pins while walking inside a stationary ring gear. Idling refers to the rotation of the planet gears on their pins whenever the planet carrier is stationary. Torque is transmitted from the sun gear to the ring gear or from the ring gear to the sun gear via the planet gears and the stationary carrier. In both cases, the driven member is turned in the opposite direction to the driving member. To provide the ratios available from the gear set, one or more of the components must be held or released. This is normally done by hydraulic servos, operated by transmission fluid under pressure, acting on lined bands or clutches, or by one-way clutches. They allow turning in one direction, but act as a lock-up or reaction member in the opposite direction. In practice, a combination of these is normally used. A simple planetary gear set can illustrate how to control individual members to produce a particular output or neutral. This planet carrier is attached to the output shaft. The sun gear is attached to the input shaft from the turbine. The ring gear is not held. When the input shaft rotates the sun gear, the planet gears idle on their stationary carrier pins and turn the ring gear in the opposite direction to engine rotation. This free rotation of the gears provides neutral. No drive is transmitted to the output. For low gear, a brake band anchored to the transmission case is placed around the ring gear. Applying this holds the ring gear stationary. Now when the sun gear rotates, the planet gears can no longer idle. They must walk around the inside of the stationary ring gear. The planet carrier must move with them in the same direction as engine rotation, but at a slower speed and with an increase in torque. A direct drive or top gear condition with a 1-to-1 ratio is obtained by locking together any two members of the gear set. A multi-plate clutch can be used for this purpose. The outer drum and outer plates are attached to the ring gear. The inner plates and inner drum are attached to the planet carrier. When fluid under pressure is directed onto the clutch piston, the clutch plates are locked together. This locks the planet carrier to the ring gear. Now when the sun gear is rotated, the planet gears can neither idle nor walk. The whole gear set turns as one unit to give a direct drive. For reverse, the ring gear is attached to the output shaft, and the planet carrier is held stationary by a brake band. Rotating the sun gear causes the planet gears to idle on their stationary pins. This turns the ring gear and its output shaft in the opposite direction to engine rotation. The simple gear set illustrates basic principles, but it can't obtain all the ratios required. In practice, compound planetary gear sets are used. The Ravigno gear set has two simple gear sets with only one ring gear. All gears are always in mesh, just as in a simple gear set. A primary sun gear meshes with short primary pinions. A secondary sun gear meshes with long secondary pinions. Both sets of planet pinions are mounted in a common planet carrier, and they mesh in pairs. The outer secondary pinions mesh with the ring gear, which is attached to the output shaft. A Simpson gear set has two simple gear sets connected by a long sun gear common to both gear sets. The sun gear is free to rotate on the output shaft. It is constantly meshed with the planet pinions of both sets. They in turn mesh with their individual ring gears. Both sets are also connected by each having a part spline to the output shaft. The ring gear of the rear set and the planet carrier of the front set. The input shaft is separate from the gear set. The drive is transmitted through one or more clutches, depending on the gear and range engaged. Two bands and a one-way clutch are also used to control the gear set components. All bands are externally contracting types and have a thin layer of plain or grooved friction material bonded onto a spring steel or cast steel backing. One end of the band rests against a stop or strut in the transmission case. The other end accommodates a push rod or linkage from a hydraulically operated servo, which contracts the band onto the drum. The simplest servo consists of a cylinder containing a piston return spring, and a push rod. Fluid leakage past the piston is normally prevented by neoprene-type seals. Fluid under pressure is directed onto the piston in the closed cylinder, moving it to apply the band. When this fluid is dumped or exhausted from the supply line, the spring returns the piston, and the flexible band springs back to its released position. In a pressure release type servo, the band is applied in the normal way by fluid pressure acting on the piston head. However, this fluid is not dumped to accomplish band release. Release is obtained by supplying fluid at the same pressure to the opposite side of the piston. As soon as pressure is equal on both sides of the piston is moved to the release position by the force of the return spring acting on the release side. The band speed of application or release is controlled by the rate at which fluid on the release side enters or leaves the servo. When admitting release fluid is unrestricted, the band is released quickly. When dumping it is unrestricted, a snap band application occurs. This is because fluid under pressure is already acting on the servo piston. Pressure release servos can also have pistons with unequal areas. In this case, the release side has a larger surface area than the apply side. The band is brought into operation by directing fluid onto the reduced area that surrounds the hollow portion, accommodating the return spring. When fluid at the same pressure is directed to the release side, the differential area results in a higher release force. The band can be released even while apply fluid continues to exert force on the piston. The fluid directed to the release side can be directed at the same time to a clutch piston to bring the next component into operation. Multiple disc clutches can be used to hold members to the case instead of using bands, but in most transmissions, they couple planetary gear members and shafts together. A servo-operated band can only hold a member stationary, but multiple disc clutches can hold or drive individual members. They have a set of driving plates and a set of driven plates collectively called a clutch pack. Both sets may be spring steel, but one has friction material bonded onto both faces. And since they operate in the transmission fluid, they are called wet clutches. The friction material may be plain or grooved. Grooving allows for fluid to escape from between the plates when the clutch engages. The steel plates may be dished or waved, with alternate high and low segments. This design promotes smooth engagement. The size and number of plates in a clutch pack depends on the maximum torque it is required to transmit. 3 to 5 plates of each type are commonly used. The plates are pressed together for engagement by a hydraulically operated piston. It moves in a short cylinder in a clutch drum or in a cylinder machined in the casing. Release can be effected by one large coil spring or by a pack containing many small springs. When a diaphragm spring is used, it gives extra leverage to increase the apply force as well as providing the release force. The outer circumference of the diaphragm spring rests against a step in the clutch drum. The piston pushes against the inner circumference of the spring to apply the clutch. The force exerted on the clutch pack is multiplied by leverage from the diaphragm as it pivots against the pressure plate. In the released position, the plates must retain a set clearance. This allows them to separate from one another and avoid excessive or premature wear. Premature wear can also be caused by partial application of a clutch at high speed. This can occur if fluid is trapped in the clutch cylinder after release. Trapped fluid accumulates at the outer portion of the cylinder. At high speed and under the action of centrifugal force, this can produce enough pressure to effect partial application. This can be prevented by a pressure relief valve in the piston. It is normally a flat reed or ball check type, which is easily closed by the apply fluid. On release, the valve is unseated by the rotation of the assembly, letting fluid escape. One-way clutches are used in the gear train to allow rotary motion in one direction only. They simplify the hydraulic and mechanical control of the members. The hydraulic control system requires a continuous supply of fluid under pressure, normally provided by a fixed displacement pump. It is driven by the torque converter when the engine is running. The pump driving member is engaged by tangs on the converter spout, or machined flats, or by slots. Pump output always exceeds normal operating demands, so pressures are controlled by regulating valves. Excess fluid returns to the pump inlet or is dumped into the oil pan, where it can reach the pump intake strainer. Crescent-type pumps are commonly used in automatic transmissions. A fully hydraulically controlled transmission controls the shift points by a hydraulic control unit or valve body. Fluid for transmission operation and lubrication is supplied by the pump. Pressure control valves determine the pressures in the system according to operating conditions. These conditions are signaled to the control valves, and two inputs are critical: engine load and vehicle speed. The engine load signal can come via a cable connected to the throttle linkage. The speed signal is provided by a governor valve attached to the transmission output shaft. In an electronically controlled transmission, the speed of the vehicle and the throttle opening are sensed by the vehicle speed sensor and the throttle position sensor. This information is sent as electrical signals to an ECU. The ECU combines this input data with information in its memory, then sends output signals to electrical solenoids in the hydraulic control unit. The solenoids control the movement of the shift valves, which in turn controls the shifting of the transmission. In fully hydraulically controlled transmissions, the driving pattern, that is the timing of upshifts and downshifts, is designed into the transmission and cannot be readily altered. In the electronically controlled transmission, the ECU can store different driving patterns. The driver can select the driving pattern that best suits driving conditions. Normal mode is a shift pattern for city, suburban, and highway driving. Gear changes are compatible with both low fuel consumption and good accelerating performance. In power mode, upshifts or downshifts occur at higher speeds than in normal mode. It suits heavy acceleration and brisk driving. Changes between ratios may also be faster and crisper. The ECU's precise control of up and down shifting to suit driving conditions means less shock going from one ratio to another. The transmission operates more smoothly. It will also select the best available ratio for a given condition, which improves fuel consumption. Anti-squat control can be provided when the transmission is placed in a drive range from the neutral position. The transmission will engage second or third gear before shifting into first gear. The input shaft attached to the turbine is still brought to a sudden halt by engaging a drive range, but the shock is absorbed by successive engagement of the gears. Some vehicles can identify and adapt to a driver's individual style and to environmental conditions. Electronic shift programs are expanded to include these extra functions. Identifying driving style means characteristic accelerator pedal movements are used to decide how the driver prefers the transmission to shift. 4 functions can be derived from these patterns. Accelerator pedal movement can be evaluated when moving the vehicle away from rest and during regular driving. The length and frequency of kickdown periods can be evaluated, and the speed of accelerator pedal movement, or kick fast. This data from a throttle position sensor, together with vehicle road speed, can identify driving style. One of 4 shift programs can then be initiated. Shift Program 1 caters for exceptional journey comfort and low fuel consumption. Program 2 for normal comfort and low fuel consumption. Program 3 is for sporting drivers. And Program 4 caters for exceptionally keen sporting drivers. Programs 1 and 2 cover the largest percentage of driving styles. Since driver responses can vary considerably within a short time, depending on traffic and road conditions, response patterns are analyzed continuously. If a driver's requirements change suddenly after a stop, the driving style identification circuits within the control unit must respond quickly. For this reason, assessment of moving the vehicle from rest takes priority over the other 3 assessments. Identification of environment means identifying unusual ambient conditions in which the vehicle is operating. Slippery conditions require a gear ratio which enhances traction and the stability of motion of the vehicle. Wheel slip monitoring via anti-lock braking sensors may confirm poor tire grip, and a winter shift program can be selected. Return to a normal gear selection pattern is controlled by a high friction function, which evaluates engine torque and wheel slip to establish when this condition has again been reached. For driving on steep gradients or with a heavy load, a performance-type shift program can prevent hunting or too frequent up and down shifts between adjacent ratios. In specific driving situations, it can be beneficial to select a gear not normally selected in a shift program. A normal shift program characteristic initiates shift changes according to road speed and throttle opening angle. Shift characteristics are arranged so that upshifts are triggered by an increase in road speed or by reduced throttle opening. Downshifts occur when the opposite situations apply. But in some situations, as when the brakes are applied, when cornering, or descending gradients, unwanted gear shifts may occur. If additional inputs are used to determine these circumstances, then an optimum ratio can be selected. 4 special functions are provided. Fast-off identification, downhill gradient identification, corner identification, and stop-and-go identification. In order to slow the vehicle, the driver lifts his or her foot off the accelerator and, if necessary, applies the brakes. In normal driving, closing the throttle prompts the transmission to upshift to a higher ratio if it is not already in top gear. In a higher gear, the engine contributes less to the braking process, and when the accelerator is depressed again, a downshift usually takes place. These unnecessary shifts can be prevented by the fast-off identification function. An intention to brake can often be detected by rapid and complete release of the accelerator. If it is identified, upshifts are inhibited until the pedal is depressed again. The fast-off identification function can also apply when the vehicle approaches a corner. Rapidly releasing the accelerator may inhibit an upshift if the vehicle is not already in top gear. But if upshift has been avoided by fast-off identification, it is still not desirable to upshift on the actual corner, even if the accelerator is depressed again. So, upshifts are prevented when a preset rate of lateral acceleration is exceeded. The radius of the curve is determined by comparing the rotating speeds of the inner and outer front wheels when the vehicle is not travelling in a straight line. This data from the wheel sensors, added to road speed, allows a sufficiently accurate estimate of lateral acceleration. If corners are taken at a particularly high rate of lateral acceleration, downshifts are also inhibited. For data from the wheel sensors to be accurate, it is essential the two front wheels have the same dynamic circumference. This is monitored continuously by the diagnostic circuits. Any discrepancies, perhaps from different tyre pressures, will deactivate the corner identification. On a downhill gradient, if an upshift occurs when the accelerator is released, there is no engine braking. To stop, the driver would need to apply greater force to the brakes. And vehicle road speed tends to increase even if the accelerator is not touched. Identifying a closed throttle and increasing road speed causes the system to respond initially by preventing further upshifts. If brakes are then applied, a single downshift takes place. Downshift only occurs below a preset engine speed. This avoids application of peak engine braking torque. The downhill identification gradient mode becomes inactive once the accelerator is depressed again. In dense traffic, only a small proportion of the vehicle's performance is needed to keep it moving. For a powerful vehicle, second gear is adequate when accelerating from a standstill. A stop-and-go situation is identified if the throttle opening angle and the road speed remain below preset limits for a given period of time. This prevents shifting down to first gear. That makes progress smoother, lowers fuel consumption, and reduces any tendency to creep forward from a standstill. When the preset load speed range is exceeded, first gear is no longer inhibited. Despite the benefits of adaptive control, a particular ratio can still be selected manually. In Steptronic applications, the manual program is available by moving the selector lever to the left of the D position. Automatic changes continue in a sport program until the lever is operated in a one-touch movement towards the manual mode. Forward movement changes the transmission to a higher gear. Backward movement to a lower gear. Overspeed protection prevents a gear engagement lower than the governed engine speed. And when a low ratio is selected for acceleration, a shift up to the next higher gear takes place shortly before the governed speed is reached. Kick down initiates downshifts in all speeds to the lowest available ratio. And at low speeds, automatic downshifts as far as third gear occur to ensure adequate traction for reacceleration. A continuously variable transmission has no fixed gear ratio changes. Changes occur in a smooth, stepless progression to suit speed and load conditions. Once a drive range is selected, a belt and pulley system continuously varies drive ratios and transmits the drive to the final drive gears. This application has an electronically controlled magnetic clutch. A small gap between the driving and driven members is filled with magnetic powder. A coil on the driving member receives electrical current via two slip rings and brushes. Current through the coil generates a magnetic force that links up the magnetic powder in a chain fashion. Torque is transmitted from the driving member to the driven member. Clutch current is controlled by a transmission computer, reacting to input data about vehicle operating conditions. At idle speeds with the vehicle stationary, current flow is small, which allows slippage between engine and transmission. As the accelerator is depressed, the computer delivers more current to the coils. The powder locks the engine rigidly to the transmission input shaft. With the engine off, or the selector in park or neutral, reverse direct current sent to the coil demagnetizes the clutch powder and releases the clutch completely. Forward or reverse motion of the vehicle is obtained by placing the selector lever in drive or reverse. In drive, a synchronizer assembly connects the magnetic clutch directly to the primary pulley of the variable transmission. In reverse, the drive is transmitted through a reverse idler. It changes the direction of rotation of the primary pulley and the transmission. A steel V-belt connects the primary pulley to the secondary. The pulleys are split to allow their contact radius or groove width to be varied. Hydraulic pressure from an engine-driven pump and a computerized hydraulic control system moves one side of each pulley inward or outward. This widens or narrows the pulleys, but the V-belt stays taut at all times. In a widened pulley, the belt rides down to the bottom of the groove. When the pulley is narrowed, it rides up to the top. This creates different size pulleys, which act like gears of different sizes to provide varying gear ratios. When the primary or drive pulley is widest and the secondary or driven pulley is narrowest, it creates a low ratio of approximately 2.5 to 1. When the pulleys are the same size, a 1-to-1 direct drive gear ratio is created. With the drive pulley narrowest and the driven pulley widest, an overdrive ratio of about 0.5 to 1 is created. Between these extremes, the variation in pulley widths provides a stepless range of gear ratios which is not linear, as in a manual transmission. It is expressed as the region, bound by the maximum and minimum pulley ratio. This allows the engine to run in its most efficient speed range for fuel consumption and maximum torque output. The steel belt consists of 280 hardened steel V-blocks held together by two endless steel bands, each made of 10 laminated strips. These strips fit closely together in a very strong and flexible ring. The blocks are guided by the bands, but not attached to them. Drive is transmitted by compressing the block elements, rather than relying on tension in the band. Each block leaving the primary pulley pushes the blocks ahead of it, to the secondary pulley, where the bands keep the blocks in contact with the pulley faces. The blocks are in compression on the drive side and float loosely along the laminated bands on the return side. The large number of blocks in contact with the pulleys keeps surface pressures low, allowing high torque to be transmitted. The belt is lubricated by transmission fluid sprayed directly onto it at high pressure. The secondary pulley shaft is splined to a helical reduction drive gear. It meshes with a similar reduction driven gear, splined to the final drive pinion shaft. The final drive pinion meshes with the final drive ring gear to transmit the drive to the differential case. Selecting D provides a normal driving mode from start-off to maximum speed. Speed change occurs between 1600 and 4000 RPM, depending on whether acceleration is gradual or rapid. At cruising speed, when pressure on the accelerator is reduced, the pulley ratio is at a maximum and the transmission is in overdrive. If the accelerator is depressed while cruising, the pulley ratio shifts to minimum and vehicle speed rises quickly. In the DS position, ratio changes can occur only in the higher zone of the speed change region. In reverse, the pulleys are locked in a low ratio position. No speed ratio changes take place. In park, the secondary pulley is mechanically locked to the transmission case.